Okay, so in the last section we talked about the sampling distributions of sample proportions. In this section we're just going to take a look at what a sampling distribution looks like for sample means. So think about the same concepts that we used in the last section, and we're going to apply them just a little bit differently to sample means, but it's still the general same idea. We're taking a bunch of statistics, we're putting them in a distribution, and then taking a look at the center, shape, and the spread of the distribution. So what we're going to do is the same thing we did in the last section, find the mean and standard deviation of a sampling distribution of a sample mean. So all of our statistics in this case are going to be means instead of proportions. Okay, now notice this is the same. Notice how it says check the 10% condition before calculating the standard deviation. So that 10% condition is telling us that the population has to be 10 times the sample size in order for each of our trials to be independent so that we can use the standard deviation. We're going to explain how the shape of the sampling distribution of a sample is affected by the shape of the population distribution and the sample size. Okay, and that's different. Remember, for sample proportions, the sampling distribution didn't really have anything to do with the population. Okay, and then, if appropriate, use a normal distribution to calculate probabilities involving sample means, which is the same process that we did in the last section. All right, so let's just take a look at the sampling distribution of X bar. So remember, X bar is a statistic that is telling us that we're looking at a mean of a sample and not a population. Okay, so how do we know when we should be dealing with sample proportions versus sample means? So sample proportions arrive most often when we're interested in categorical variables. So that's like the proportion of students that own iPhones versus Androids, the proportion of students that have red hair, stuff like that. So those are all categorical variables. I can sort of put them into bins. Sample means are when we're talking about quantitative variables, and we're interested in other statistics such as the median or the mean or the standard deviation of the variable. Okay, so this is we're going to talk about the average number of iPhones in a household, the average number of TVs in a household, something like that. Okay, so let's take a look at an example. So consider the mean household earnings for samples of size 100. So what that means is we're taking a sample of a size 100, we're going to find the mean household earning. We're going to do that a second time. Take a sample of size 100, find the mean for that one, do a third time. Okay, so we're taking multiple samples of size 100 and finding the mean household income. We're going to compare the population distribution on the left. Okay, so the population distribution would mean literally taking every single solitary household and put their earnings down. We're not taking an average, it's just literally like a list of households, their average income on a graph, okay? How does that compare to the sampling distribution on the right? So the sampling distribution is taking a size 100, finding the average household income for size 100, putting that sampled statistic or X bar on a distribution. So let's see what the graph looks like. Now look at the population distribution. The population distribution is slightly sort of skewed to the right. Okay, here's your mean mean amount of money that each household earns. Okay, so this is, like I said, literally the population, every single household with the amount of money they earn. Okay, now take a look at the sampling distribution. The sampling distribution is much less variable. There's a much smaller spread. The standard deviation is much smaller. Okay, so this was taking samples of size 100, finding that mean X bar and putting it on a graph and doing that a whole bunch of times. Now notice that the scales are the same. Because both histograms use the same scale, okay, on the X and Y axis, it's easy to compare the two histograms. So notice how the sampling distribution, this looks approximately normally distributed, while the population distribution is sort of skewed to the right a little bit. And we're going to talk about what to do with that in upcoming slides. Okay, so we're going to discuss in the upcoming slides what do we notice about the center, the shape, and the spread of the population distribution versus the distribution, the sampling distribution. Okay. Okay, so what do we notice about the center, the shape, and the spread of the population distribution versus the sampling distribution? All right, so here, now this information was just calculated. You wouldn't necessarily be able to tell that just by looking at the graph, but it was calculated from the data. Both distributions are centered with a mean of 69,750. So they both have a mean that's at the exact same place, okay? And that sort of makes sense because if I have the entire population here, okay, and I find the average, okay, that's 69,750. Think about the sampling distribution. I'm taking all possible samples of size 100, finding that average, putting it on the graph, finding another average, putting it on the graph. So this is the mean, essentially, of the sampling distribution, is the mean of all of the means that you have. So it's like a double mean. It's like the average of the averages. And since the data for your sampling distribution came from the original population, all the same numbers are in both graphs. So since the same numbers are in both graphs, we're going to have the same mean in both places. Okay? So the shape of the distribution of earned income is pretty strongly skewed to the right. However, we said before that the sampling distribution is roughly symmetric or approximately normal. The spread of the distribution of earned income is pretty spread out. So we already said this had a lot more variability, but the sampling distributions is much less spread out. And we're going to talk about why in a second. Why is this much less spread out than the population distribution? Okay, so what does all of that mean? We want to make sure that we understand the difference, okay? Number one, when we choose many simple random samples from a population, we're taking a look at the sampling distribution, okay? The sampling distribution of a sample mean, so that means literally, like I said, we're taking groups of 100, finding the sample mean, putting it on a distribution. When you do that many, many times, you get a sampling distribution with the following characteristics. The sample mean, okay, is centered about the population mean mu. So that just means that the sampling distribution has the same mean. The center of that distribution is the same as the center or the mean of the population, okay? The mean, the sampling distribution, is going to be less spread out than the population distribution. And let's just think about why. Since all of those are a bunch of averages, when I take 100 salaries and I'm averaging the lower salary to the higher salary, they kind of balance each other out, and they're going to put the X bar closer to the population mean. Okay, so here are some facts. Number one, suppose that X bar is the mean of a simple random sample of size n. So that's just one of the means, one of the sample means that you're putting in your sampling distribution. And it's drawn from a large population. We know the population has mean mu and a standard deviation sigma. The mean of the sampling distribution of X bar is the same as the population mean. Now, how do we get the standard deviation? The standard deviation of the sampling distribution of X bar, notice the notation here, standard deviation of X bar. It's really important that you put that X bar there and the mu of X bar there, super important. Mu says we're looking at the population. Mu of X bar means I took a whole bunch of samples, found the mean, put them on a distribution. Same thing here. This tells us that I'm looking at a sampling distribution with this X bar. If you don't have that, it's assuming it's looking at the population, not the sampling distribution. So the standard deviation of my sampling distribution is sigma divided by the square root of n. Now notice, okay, why is my standard deviation smaller? Because I'm dividing by the square root of n. Okay, so the larger my sample size, the smaller my standard deviation, as long as the 10% condition is satisfied. So this is basically saying that the population is 10 times the sample size, and that each of my values are independent. All right, so what does this mean? These facts are true about the mean and standard deviation of X bar, or your sampling distribution, no matter what shape the population distribution has. So that basically means if my population distribution is highly skewed to the right or skewed to the left, or whatever, has some crazy shape, that when I create a sampling distribution and take the averages, I'm going to get a graph that has a mean that's the same as the population mean and a standard deviation that's the population standard deviation divided by the square root of n. Okay? All right, so what's going to be on the AP exam formula sheet? Number one, you're given this information. You're given the mean of the sampling distribution of x bar and the standard deviation of the sampling distribution of x bar. So just make sure that you know what those mean when you see those on the AP exam formula sheet. Also, just make sure that you're really careful with your symbols. Get used to writing mean of x bar, standard deviation of x bar. All of the symbols are going to have specific and different meanings. Just make sure you use that notation correctly, or don't use the notation at all, because you will lose credit if you have incorrect notation. All right, so let's just take a look at finding the mean and standard deviation of x bar. Suppose that the number of movies viewed in the last year by high school students has an average of 19.3. So be able to recognize that that's the population mean, and a standard deviation of 15.8. That's the population standard deviation. Suppose we take an SRS of 100 high school students and calculate the mean number of movies viewed by the members of the sample. Now, hopefully you'll read this and say, suppose we take an SRS of 100 high school students and calculate the mean. So when we say we're taking an SRS of 100 high school students, that should say, hey, wait a second, we're talking about a sampling distribution of a sample mean. Okay, how do we know it was a mean and not proportion? We have this word average, 19.3. That's a quantitative variable. That's not really a categorical variable. Okay, what is the mean of the sampling distribution of x bar? Okay, what is the standard deviation of the sampling distribution of x bar? When you find the standard deviation, you must always check to make sure that 10% condition is met. That allows us to say each of my trials are independent. Okay, so we said that since we're assuming x bar is an unbiased estimator, the mean of the sampling distribution is equal to the mean of the population, which is 19.3 movies. Okay, before you find the standard deviation, check the 10% condition. So this is telling us that it's met because there are more than 10 times 100 or 1,000 high school students. Notice the notation, sigma of x bar, standard deviation of the sampling distribution, is my population standard deviation, 15.8, divided by the square root of 100, which is 1.58 movies. Okay, and notice how that standard deviation is much smaller for the sampling distribution than it is for the sample means. Okay, now what we've done so far is we've described the mean and standard deviation of a sampling distribution of the sample mean, x bar, but not the shape. Okay, so we've said that the mean and standard deviation are the same no matter what the population is. How do we know what the shape is of my sampling distribution? Okay, so the shape of the sampling distribution x bar does depend on the shape of the population distribution. How will we be able to tell? Because notice on that first slide the population was right skewed, but the sampling distribution was approximately normally distributed, very symmetric. So how are we going to be able to tell if my sampling distribution is approximately normal? Suppose that a population is normally distributed with mean mu and standard deviation sigma. Then the sampling distribution has a normal distribution with mean mu and standard deviation, provided that the 10% condition is met, and that's just always true for your standard deviation. So what this is telling us is if your population is normally distributed, then your sampling distribution is going to be normally distributed. Okay, that's awesome. Perfect. Now, note that the mean and standard deviation are true if the population is normally distributed. If the population is not normally distributed, no matter what the sample size, the sampling distribution will be approximately normally distributed. So if the population is normally distributed, and I take simple random samples of size 5, find the average, or simple random samples of size 25, or 100, or 3, or whatever, then the sampling distribution will always be approximately normally distributed. Okay, so now what is the shape of the sampling distribution of sample means when the population isn't normal? Because it's not always going to be normal. Income is usually skewed to the right. Okay, very few people make high amounts of money. Now, it is interesting that as the sample size increases, then the distribution of sample mean changes its shapes. It looks less like that of the population and more like a normal distribution. So think back to that first slide. Our graph was skewed to the right for the population distribution, but the sampling distribution was approximately normally distributed. Well, how will we know when it's going to sort of change shape? So when the sample is large enough, okay, in that case we took samples of size 100, found the mean of 100, put on the graph. Another sample of size 100, found the mean, put on the graph. When that sample size is large enough that you're going to find the mean of and put that on the graph, the distribution of sample means is going to be very close to normal, no matter what the shape the population distribution has, okay? As long as the population has a finite standard deviation. So it's basically just saying that it's not completely spread out forever and ever in both directions, okay? So what this is telling us, actually we're going to go over this in the next video. So be ready for this slide.